Hi again. This lecture, hopefully a short lecture, will cover the second question from the 2019 exam, which was entirely on the subject of Hartree-Fock, so I thought it would be a good idea to do it now. Okay, let's get going. The first part of the question, explain what is meant by a Hartree-Fock approximation. There are probably various answers that would have been acceptable. Probably the cleanest is to say that it's a variational approach, variational approximation, where let's see, where we find where the trial wave function is a single Slater determinant, is a single Slater determinant. That's probably sufficient. Or another way of saying that is that the Hartree-Fock approximation, the solution of the Hartree-Fock equations, is the lowest energy single Slater determinant that one can find, considering all possible orbitals you can put into a single Slater determinant. Also acceptable would have been to say that you have a 4 Fermi term, Cl, and that gets replaced by a mean field terms like this, Cl like this. Let's see, this term that I just wrote would have come in with a minus sign because we had one commutation of k through j to get this, plus, okay, there's 4 such terms. I guess there's C dagger I, Cl, C dagger j, Ck. I guess there's the other way around, plus C dagger j, Ck, C dagger I, Cl, and I guess the other one that we just missed was minus C dagger j, Cl, C dagger I, Ck. So making this replacement as a mean field approach also gives you Hartree-Fock approximation. So those are two possible answers, which are both perfectly acceptable. Part 2. Consider a Hamiltonian of the following general form. This is the general form we've been considering for the last 2 or 3 lectures. There's a non-interacting single body term and a 2-body term here, 4 fermions, 2 fermions, where the C and C daggers are fermion creation and annihilation operators. I and J and so forth represent arbitrary orbitals for a fixed number n of electrons in the system. Give a set of self-consistent equations whose solution would give the Hartree-Fock ground state of the system. There's a lot of homework problems on this, or some homework problems on this, and we derived this in lecture, so I'll just write out the answer. We said that the Hartree-Fock Hamiltonian will look like, well, okay, we can write it this way. H Hartree-Fock is HAB plus FAB, I guess sum over A and B, C dagger A, CB, where FHAB is the same non-interacting single body Hamiltonian, written up here, and FAB is this mean field thing that we calculated. It'll be a sum over C occupied orbitals, VACBC minus VACCB. So this is the first term being the Hartree term and the second term being the Fock term. So the self-consistent solution of these 2 equations, it gives you the Hartree-Fock ground state, where you are meant to fill up the fill lowest n orbs of H Hartree-Fock. And we know when we have a converged solution because H Hartree-Fock will become diagonal, HF diag at solution. Okay. I mean, I guess further we wrote, I mean, this is probably not necessarily to even write this, but the Hartree-Fock orbital energies that we wrote down became this form equals h mu mu plus sum over nu occupied v mu nu mu nu minus v mu nu nu mu. Okay. Anyway, this last line is probably not essential. Part of the answer. I think the things above are probably sufficient. Okay. So far, this has been pretty easy. Okay. Now we start actually getting some real physics. Consider that now the two-site Hubbard model for spinful fermions. Okay. Hubbard model. It has a hopping term, two-site hopping term, and an on-site interaction U whenever there's an upspin and a downspin on a site I. Without generality, we assume T is real and T is greater than or equal to 0 without loss of generality. Consider this case of n equals 2 fermions. By explicitly constructing the ground state wave function, so we're meant to actually find the exact ground state wave function. We're supposed to show, which is generally kind of difficult, but it's actually not that difficult. The entire size of the Hilbert space is two particles. So okay, how many orbitals do we have total? We have 4 orbitals total here. We have spin up and spin down on site 1, spin up and spin down on site 2. That's 4 orbitals total, filling 2 out of 4 orbitals. That's 4 choose 2, or 6 states in the Hilbert space. So one can generically diagonalize this Hamiltonian with a 6x6 matrix, which sounds pretty hard, but in fact it's a little bit easier than that because this will end up being block diagonal and in several senses, so it will break up and be easier than you expect. But you're not even asked to do anything that hard. You're just supposed to consider some limits where things here are quite easy. Show that for U equals 0, the Hartree-Fock approximation gives the exact ground state energy. Well, this is pretty trivial because for U equals 0, you just have non-interacting fermions. Let me write that out. U equals 0, non-interacting fermions, int fermions, and so the ground state is just a Slater determinant of the lowest 2 orbitals. So I guess we can write the lowest 2 orbitals. D dagger sigma is 1 over square root of 2. C dagger sigma 1 plus C dagger sigma 2. This is symmetric superposition. Of the 2 sites, which is just the ground state. If T is positive, that's the ground state of this hopping Hamiltonian only. And so filling up both spin up and spin down, D dagger up, D dagger down on 0 is the ground state, and that's the exact ground state when U is 0, and that is a single Slater determinant, and therefore it is the Hartree-Fock solution also, because Hartree-Fock is the best single Slater determinant. If the actual ground state is a single Slater determinant, then it is also the Hartree-Fock ground state. And so you get the exact solution from Hartree-Fock. So that one was easy. Show that for T equals 0, the Hartree-Fock approximation gives the exact ground state for both U greater than 0 and U less than 0. Okay. Oh, and there's this other comment down. What is the ground state degeneracy in each of the cases we just considered? So this ground state, the one we just calculated in part 1, the ground state is unique. Ground state is unique. Now let's go on to part 2. So let me rewrite the Hamiltonian here, because when we set T to 0, to make our life easy, so rewrite the Hamiltonian. It's U times the sum over both sides I, C dagger I up, C I up, C dagger I down, C I down, and no hopping between sites at all, which simplifies the problem enormously. Which one do you think is easier to consider? Actually, maybe u less than 0 is easier to consider first. So for u less than 0, the way you minimize the energy of the entire system is to put both spins, both particles with opposite spins on the same site. So the ground state, exact ground state, is then C dagger, say 1 up, C dagger 1 down on 0, or we put them both on the second site, C dagger 2 down on 0. Both of this, so this is twofold degenerate. Twofold degenerate. There's obviously no way you can make the energy lower than, there's no way to pick up any energy from the hopping term, because there is no hopping term, and it's obvious that the lowest energy you can get from this is when, if you use negative, is to put both fermions on the same site. So there's and both of these are Hartree-Fock, are single-slated determinants as well. They're written as single-slated determinants exactly, and so Hartree-Fock again gives the exact ground state. So now let's try the case of u greater than 0. With u greater than 0, what you'd like to have, I mean, the minimum energy you can possibly have is now 0 if you completely avoid, if the two electrons completely avoid each other. So there's actually 4 ways to do this. You could have C dagger 1 up, C dagger 2 up. So you put one particle on one site, one particle on the other site, and with the two particles on opposite sites, this term will be 0. But you could also have them with you can change the spins around. C dagger 1 up, C dagger 2 down on 0, or the other way around. C dagger 1 down, C dagger 2 up on 0, or C dagger 1 down, C dagger 2 down on 0. And since there's no hopping, these are eigenstates, and they have the minimum possible energy, and they're all single-slated determinants. It's fourfold degeneracy. Fourfold degenerate. Okay. Okay. So this much, I hope, has been easy. Now the hard part is the last part of the problem. The last part of the problem is to consider the case with n equals 2 fermions again, but we're going to consider the case of u not equal to 0 and t not equal to 0. Let me just copy the Hamiltonian here again. See if it will let me do this. It may or may not allow me to do this. Copy. Maybe I will. Okay. And paste it down here. We're going to need this. Paste. Oops. No, it won't. I have to. Okay. Let's write it out then. Okay. So the Hamiltonian is minus t sum over I, C dagger I, sum over sigma, I guess. Sum over sigma, C dagger 1 sigma, C 2 sigma, plus C dagger 2 sigma, C 1 sigma, and then plus sum over I, U out front, C dagger I up, C I up, C, these are I's, C dagger I down, C I down. Okay, just rewriting the Hamiltonian there. So maybe I mean, this isn't asked in the problem, but in fact, life was a lot easier if you realize that we know a lot about this Hamiltonian just because it is it's translationally invariant. what do I mean by it being translationally invariant? That's not obvious that it's translationally invariant, but you remember that when we looked at the Hartree-Fock problem, in general, we consider Hartree-Fock on a translationally invariant system, and we discovered that the Hartree-Fock ground state and the non-interacting ground state were the same. That it was still the Hartree-Fock ground state was just a superposition of plane waves. Now, this Hamiltonian may not look like it's a translationally invariant Hamiltonian, but actually it is. It looks like we have two sites here, and they're coupled together with a hopping T. And that doesn't look like it's translationally invariant. But if I had three sites coupled together with a hopping T, you would say, oh, I have a ring, and it's translationally invariant around the ring. I can turn this to ring around the cycle. I think there's a homework assignment working through this three-ring cycle here, three-ring circus, and maybe there's a homework assignment on that. I can't actually remember. But the this is then obviously translation invariant under lattice translations. And what about this? Well, this guy, what you want to do is you want to think about the two-site problem as actually also being a ring, and the way to do that is to sort of redraw it sort of sneakily as here's two sites, and make this hopping T over 2 and this hopping T over 2, and it's two sites around a ring as compared to three sites around a ring, and it's translation invariant. So immediately that by this principle that if you have a translationally invariant Hamiltonian, the Hartree-Fock ground state is going to be a you should be able to write it in terms of plane waves. So before even doing any work, I know that what the Hartree-Fock ground state is going to look like. It's going to be a Slater determinant of plane waves going around this cycle, and the two possible plane waves are the non-interacting eigenstates of the two-site problem, and the non-interacting eigenstate of the two-site problem are just the symmetric and antisymmetric superpositions. So I know that the Hartree-Fock ground state, without doing any work, is going to be filling up either symmetric or antisymmetric superpositions of non-interacting fermions. Okay, so that's actually really nice, and we could use that to our advantage. If you didn't realize this, we can still. I think the question is trying to walk you through this problem in another way, by showing you various symmetries one at a time, so that eventually you figure out what the Hartree-Fock ground state is supposed to look like. But really, we should have been able to do it by inspection. So let's just go through the problem bit by bit. So for the case where u is not equal to 0 and t is not equal to 0, I just want to move myself out of the way here. Okay, for the case where u equals 0, u is not equal to t is not equal to 0, the ground state is never degenerate. You can take this statement as given, so it's a gift. You don't have to worry about ground state degeneracies. Give an argument that the exact ground state in this case must be spin 0. Well, another feature that we should recognize from our Hamiltonian is this Hamiltonian is rotationally invariant in spin space. H is rotationally invariant in spins. So if you rotate all the spins, the Hamiltonian is unchanged. So how can we show that? Well, maybe the easier term to consider is the u term, and the reason that this is rotationally invariant is the u term here. It gives you an energy u whenever there's two fermions on the site. And it doesn't matter if you describe the two fermions on the site as a spin up fermion and a spin down fermion. on the same site, or an X plus fermion and an X minus fermion, or a Y plus fermion and a Y minus fermion, or any axis you want, this Hubbard interaction term is completely rotationally invariant. Similarly, this hopping term, well, this again, it looks like this hopping term tells you should hop the upspin and you should hop the downspin, and you should add them together. But if you rewrite the instead of in the up and down basis, you write in the X plus and the X minus basis, you'll discover that this term here is entirely equivalent to saying hop the X plus spin and hop the X minus spin. You can make a rotation of both of these terms, and the Hamiltonian stays exactly unchanged. So that's a big hint. And once we know that Hamiltonian is rotationally invariant, we know that the ground state must be a singlet or a triplet, This is just, if we, if you have a rotationally invariant Hamiltonian and you have two spins, it doesn't even matter what the Hamiltonian is. If you have two spins and the Hamiltonian is rotationally invariant, the ground state has to be either a singlet or it's a triplet. It has to be L equals 0 or L equals 1. Those are the only two possibilities. Now, you're told that the ground state is non-degenerate, which means it can't be the triplet. So this one is gone, and so if the ground state is non-degenerate, it must be a singlet. Okay, good. And if the ground state is a singlet, it must mean that the spin is 0. Argue that the Hartree-Fock ground state with 0 spin must be expressible in the form F1 dagger, F2 dagger on 0, where F1 dagger is an upspin, some superposition of the upspins, and F2 dagger is some superposition of the downspins. Well, okay, one way of doing this is saying, let's write my Hartree-Fock ground state. I know it's going to be some superposition of F1. I have to be able to write it in terms of two orbitals, two creation operators on 0 equals Hartree-Fock ground state. I should be able to write it in terms of two creation operators. I don't know what the creation operators create, but they create two things in two orbitals. But I know if I have a singlet that there cannot be, when I convert to the original basis of the C daggers, there cannot be any spin up terms, because that would not be compatible with having something be a spin singlet. This is a part of a triplet. So that means I have to be able to write F dagger 1, F dagger 2 in F dagger 1, F dagger 2 that does not create spin up. Well, the only way that happens is if can only be true if F1 creates up and F2 creates down, or the other way around. F1 creates down and F2 creates up. So this is exactly the form that we wrote here. It has to be some the F1 has to be create up, and F2 has to create only down. Okay, so we know immediately that we have a Hartree-Fock ground state, which is F1 creating some spin up. Let me actually write down F1 creates spin up. What did I call it? Alpha. What's the notation? Alpha and alpha prime. Alpha C dagger 1 up plus beta C dagger 2 up, and F2 dagger is alpha prime C dagger 1 down plus beta C2 down. Now again, I actually know, because at the very beginning of solving this problem, we know what the Hartree-Fock ground state is going to be anyway. We know it's going to be a superposition of either, it has to be the superposition of two of the non-interacting eigenstates because of this translational invariance feature that I mentioned. But the question is sort of saying, let's use symmetries to prove that this must be true. So using the symmetries of the Hamiltonian, can we prove that alpha and beta represent non-interacting eigenstates, that these F's create non-interacting eigenstates of the system, and that gives you the Hartree-Fock ground state. Okay, so there's a couple of steps that we can use to prove this using other symmetries of the system. Probably it would be much easier to just realize this translational invariance. But first of all, the Hamiltonian is time reversal invariant, is T invariant, which means the wave functions can be taken to be real. So alpha, beta, alpha prime, and beta prime can be taken to be real. That's and arbitrarily we can always choose alpha and alpha prime to be positive or non-negative, greater than 0. This is just an overall phase, because if alpha came out negative, I just multiply. So if I had something with alpha negative here, I could just multiply the entire creation operator by -1. That's another acceptable creation operator. It creates the same orbital with just a different phase reference, so that I can always choose alpha to be positive, but then beta could be positive or negative. Furthermore, the Hamiltonian is right-left symmetric. So that tells me that, let's see, does that tell me, okay, so the Hamiltonian is both right-left symmetric and rotationally invariant in spin space. So we're using the rotational invariance in spin space, which tells me that we better have absolute alpha equals absolute alpha prime equals absolute beta equals absolute beta prime. And by normalization, this better be 1 over square root of 2. So this leaves us with the only possibilities of wave functions that look like 1 over square root of 2, C dagger 1 up plus or minus C dagger 2 up, and similarly for down. And this is not surprising, because these are the non-interacting orbitals, and these are the only possibilities. Okay, so you have to fill non-interacting orbitals because of this translational invariance. Finally, the last question for u not equals 0 and t not equals 0: is the Hartree-Fock approximation ever exact? Well, the answer is no. And to prove it's not exact, here we have okay. So the a single particle basis is you have, okay. Let me change some notation here. Let's call the F's the F dagger up is going to be the symmetric superposition, and G dagger up is going to be the okay, so F dagger sigma will be the with spin sigma, it's the symmetric superposition with spin sigma, and G dagger sigma will be the anti-symmetric superposition. Okay, so these operators span the entire Hilbert space. We can create everything. This is a way to describe the Hilbert space in terms of these F and G operators. And the claim is that the Hartree-Fock ground state is going to be something like F up, F down on 0. So that will be the symmetric superposition of both. It depends on whether this T is positive or negative, whether you get a superposition of the F's or the superposition of, you get a product of F's or product of G's, at least for small values of U. But okay, let's assume this is the Hartree-Fock ground state in this case, and the question is, can that be ever exact? Is this exact? exact for u not equal to 0 and t not equal to 0? The answer is no. So this term here is a diagonal for the hopping term. This is an eigenstate of the hopping term only. And the ground state will be exact if it's also an eigenstate of u. So what we have to do is we have to check f dagger up, f dagger down 0, and then the u operator, h int, here. And does this thing give me back exactly the same? Does it give me back f dagger up, f dagger down on 0? Okay, so well, we can try to figure out. Basically, what we do is we write out this Hamiltonian. We write out this wave function, apply h int, the Hubbard interaction to it, and see if it gives back the same wave function. It does not. It's fairly easy to convince yourself of that, that it does not give back the same interaction, because this term is, okay, let's write it out in terms of the c's. So it'll be c dagger 1, okay, it'll be c dagger 1 up plus c dagger 2 up, 1 over square root of 2, 1 over square root of 2, c dagger 1 down plus c dagger 2 down, all in 0. And the interaction term, I'll move myself out of the way. The interaction term here gives an energy u to, okay, so this product here has 4 terms, these 2 terms times these 2 terms, and in the product there's 2 terms that get a coefficient of u because they have 2 particles on the same site, like 1, 1 and 2, 2 get an energy u because they have 2 particles on the same site, whereas the cross terms have 2 particles on opposite sites and they do not get an energy of u. So therefore, this f dagger is not an eigenstate of the interaction term of the Hamiltonian, so the Hartree-Fock ground state is not an exact ground state of for t not equal to 0 and u not equal to 0. And that is the end. Okay, so I realize that the last question was a little bit long and rambling. It was probably a difficult question. This last part was probably difficult. Some students did actually more or less get it right. I don't, if I remember correctly, I don't think any students used the translational invariance trick, which is sort of not, I mean, you're sort of not led along that direction of trying to identify the translational invariance. But that would have been the easy way to sort of shortcut the whole thing and know exactly what the result was going to be immediately. But even without knowing it, it's doable, but it definitely is tricky. But some students more or less got it right. Okay, so I'll stop there. In next lecture, we will consider screening and electromagnetic response of interacting Fermi systems. See you then.